In this video, we're going to be talking about finding limits and determining the continuity of multivariate functions. So I'm going to start by just defining a limit. And so what I have on the screen, some of you may have seen this, some of you may have not, but this is actually the more precise or the formal definition of a limit. So when you first learned about limits, you probably learned that limits describe what happens to the y values as you approach a certain x value. So for example, on this picture I have on the screen, as we approach this x value of a, it looks like the y values are approaching some number L. And so we say the limit as x goes to a of this function is L. So that's what we mean by a limit for a function of one variable. And then just below that, I have the formal definition of a limit. It says for every epsilon bigger than 0, there exists a delta bigger than 0, such that the distance between x and a is less than delta for all x in the domain of f, when the distance between f of x and L is less than epsilon. And so that's a lot of words. That's a formal definition of a limit. It basically means that we can get as close to L as we want, any epsilon, so epsilon is a really tiny number, we can get as close to this L value as we want by picking a sufficiently small delta. And that's our formal definition of a limit. Now, the reason I bring this up is because I want to show you the definition of a limit for a multivariate function. And so it helps to kind of remember, or at least see, what exactly do we mean by limits for functions of one variable. Okay, so if we want to find the limit for a function of two variables, so our function of two variables is a surface, and that's what I have drawn on the screen. So there's our function, our surface. The idea is we want to approach our point, so we're approaching some x and y value, some point. So we're going to approach some point and see what happens to, I guess in this case it would be the z values. And so we're going to define what's called a delta neighborhood. And basically what that means is you could imagine that to find this limit, think about creating a disk or a circle around that point that we're interested in, and then thinking about, well, what happens as that circle gets smaller and smaller and smaller as we actually approach that point. So here's our definition for the limit of a function of two variables. And so I'm not going to read all of this. I have it on the screen so that you can read it, and I can definitely kind of talk through some of this notation if anyone's interested. But in this class, we don't have time to talk about the formal definition of these limits. The important thing I have on this slide is basically, as we approach this point, from any direction, if the z values approach some number z equals L, that's what our limit is equal to. Okay, so again, this definition is saying that we can create kind of a disk or a delta neighborhood around that point, and if we make that delta neighborhood sufficiently small enough, we should be able to get as close to that L value as we want. Okay, again, that's a lot of words. I know this formal definition of limit is something that even in two dimensions, some of you maybe haven't seen before. But I have circled the important concept here is when we're finding the limit of a function of two variables, we're finding the limit for a point, an ordered pair, an x and a y. And as we approach that point from any direction, we want to see what happens to those z-values. And if those z-values are always approaching some number, say L, that's what our limit is equal to. All right, so how do we actually find limits for multivariate functions? Well, it turns out we have a bunch of limit laws, just like we did when we were working in 2 dimensions. So the limit of a constant is a constant, for example. Or if we want to take the limit of a sum of functions, we can find the limit of each and then add those together. And basically, I'm going to go through this kind of fast. This is all in your textbook if you want to look at it later. But basically, all of these limit laws I have on the screen are analogous to the limit laws that you learned when you found limits for functions of one variable. And basically, what all these limit laws ended up telling us is that if we want to find the limit of a function, whether it's a function of one variable or 2 variables, we can frequently use direct substitution. We can just plug the numbers in and see what we get. And the only time that's not going to work is if we end up getting something that's indeterminate. And so those indeterminate forms are 0 over 0 or infinity over infinity. There are some other indeterminate forms you've probably learned as well, and those apply here. But we're going to just kind of focus on the 0 over 0, infinity over infinity for now. All right, so finally, this is kind of a long formal introduction. Let's actually do some problems. So how do we find limits of these multivariate functions? So for example, let's find the limit as x and y goes to 2, 1. So we're approaching the point 2, 1 of the function x squared plus y over 3xy. So the very first thing I'm going to try for any limit problem is I'm just simply going to try what we call direct substitution, or just plugging the numbers in. And so if I plug in 2 for x and 1 for y, I end up getting 2 squared plus 1, which is 5, over 3 times 2 times 1, which is 6. And that's my answer. The answer to this limit is 5, 6. So as we approach the point 2, 1, our z-values, or our outputs, approach 5, 6. And again, this direct substitution is going to work unless we get one of those indeterminate forms. And so for my second example, let's see what happens when we plug the numbers in. So now we're finding the limit as we approach the point 2, 1 of x minus y minus 1 over the square root of x minus y minus 1. So if I plug my values in, I end up getting 0 divided by 0. And this is indeterminate. This means we don't know what the answer is. We have more work to do. And just like when you first learned about limits in Calc 1, we can use the same techniques for these multivariate functions. And by the techniques that you learned in Calc 1, I'm talking about things like factoring, rationalizing the denominator, rationalizing square roots, maybe simplifying complex fractions. Basically, it all boils down to doing algebra, seeing if you can simplify the expression. And so for this particular problem, I am going to try to rationalize the denominator by multiplying the top and bottom by the conjugate. So if I look at the denominator, I have the square root of x minus y minus 1. And so the conjugate, I just simply change the minus sign that's between the square root and the number to a plus sign. And I'm going to multiply the top and bottom by that expression. And so now I'm left with limit as xy goes to 2, 1. And on the top, I just copied down the two factors that we're multiplying together. So it's x minus y minus 1 multiplied by that square root x minus y plus 1. And then on the bottom, I'm going to use that difference of squares formula to multiply my square root minus 1 times my square root plus 1. And I'm going to end up with that square root squared minus 1 squared. And that turns into an x minus y minus 1 in the denominator. Finally, looks like we have a common factor in the top and the bottom. We can cancel out that x minus y minus 1. And I'm left with limit as xy goes to 2, 1, square root x minus y plus 1. And then finally, let's plug those numbers in, see what we get. I get square root of 2 minus 1, that's root 1, or 1, plus 1 is 2, and so my final answer here would be 2. Here's another one. Limit as xy goes to 0, 0 of 2x plus 3 over x squared plus y squared. So once again, the first thing I'm going to do is just plug the numbers in. And so when I plug 0, 0 in, let's see, I end up getting 3 divided by 0. And we can't divide 3 by 0. 3 divided by 0 is undefined. This is technically not indeterminate because we have a number, a non-zero number on the top. 3 divided by 0 is undefined. And so we can just say the limit doesn't exist. Technically, these function values are going to grow without bound or approach infinity. When you take 3 divided by a very, very tiny number, you're going to get something that's very, very large. So this limit doesn't exist. The z values are approaching infinity. One more example. Limit as xy goes to 0, 0 of x minus y over x plus y. If we plug the values in, we do get 0 over 0. That's our indeterminate form. And so in this particular case, there's not really a ton of algebra I can see to do here. And so instead, I'm going to see what happens as I approach this point from several different directions for this function. So what do I mean by that? I mean, let's start by seeing what happens when we approach the origin, the point 0, 0, along the x-axis or along the line y equals 0. And that's what I have drawn on the screen. So what happens if we just look at this kind of slice of our function that goes along the line y equals 0? What happens as we approach the origin? Well, to answer that question, I am going to take y equals 0 and just plug that into my function. So I'm going to replace those y values with 0 and then see what I get. So now this function along the line y equals 0 has turned into x minus 0 over x plus 0, or x divided by x. And so let's find the limit as x goes to 0 of x divided by x. Well, x divided by x simplifies down to 1. We have a limit of a constant. The limit as x goes to 0 of 1 is just 1. So as we approach the origin, along the line y equals 0, the z values are actually approaching 1. Now, this isn't enough to say the limit is 1. We need to somehow see what happens in other directions. And this limit is only going to equal 1 if the z values approach 1 from every direction. So we're not going to check every single direction, but let's check what happens along x equals 0. So if we approach the origin along the y-axis where x equals 0, what do we get? And so I went ahead and I took this function, I plugged 0 in for the x's, and this problem simplified down to the limit as y goes to 0 of negative y divided by y, which actually simplifies to negative 1. So as we approach the origin along that line y equals 0, or I'm sorry, we're on x equals 0 now. Yeah. As we approach the origin along that line x equals 0, our z-values are actually approaching negative 1. Because these numbers are different, that means this limit doesn't exist. We could have checked in another direction as well, but once you find that two different directions give you different limits, that's enough to say that your limit doesn't exist. But I could have also approached along another path. For example, the line y equals 2x is a path that goes through the origin. So basically, I could have approached from any path that goes through the origin. I have my work written down if you want to approach along the line y equals 2x. You would just go ahead and replace all the y's with 2x's and then simplify that expression. In this case, it's simplified down to negative 1/3. So as we approach along y equals 2x, my z-values are approaching negative 1/3. That's yet another different number. This limit definitely doesn't exist. So one great way to show that a limit doesn't exist for multivariate functions is to check and see what happens as you approach from several different paths. So along several different lines, that pass through that point that you're interested in. Now I want to briefly talk about the idea of continuity in this video as well. A function of two variables is continuous at the point a, b, if the limit of that function is also equal to the function value. We had a definition in Calc 1 that was very similar. We defined continuity for a function of one variables in really the same way. A function is continuous if its limit is equal to its function value. Basically, that means the function isn't going to have holes or gaps or jumps in it. So in order for a function to be continuous, it means the function must be defined at the point that you're interested in. The limit must exist at that point. And both the limit and the function value must be the same number, must equal the same thing. So if we want to find the continuity of these functions, we're going to do something similar to what you did in Calc 1 when you first talked about continuity. The functions that we're working with are going to be continuous on their domains because on the domain of these functions, to find the limit, you can use direct substitution. You just plug the numbers in, and so the limit and the function values are going to be the same on their domains. Okay, so for part A, again, we have a rational function. Rational functions are always continuous on their domains. And so to find the domain of this function, the denominator can't equal 0. We can't divide by 0. So that means x squared plus y squared cannot equal 0. And x squared plus y squared will only equal 0 when both x and y are 0. Because when you square a number, you always end up getting a positive or maybe 0. And so the only way you can add together two squares and get 0 is if they're both equal to 0. So both x and y have to equal 0 for the denominator to be 0. So that means this function is continuous everywhere except at the point 0, 0, because that point is not in its domain. My second example is the function f of xy equals sine of x plus y. Where is that function continuous? This is just a sine wave. So what's the domain of a sine wave? Well, the domain would be all real numbers, and I put an R2 there to indicate that the domain is a set of x's and y's. It's a plane, so our domain is all real numbers, and that means this particular function is continuous everywhere. So if we want to determine where a function is continuous, if we're talking about rational functions, trig functions, logs, exponentials, polynomials, square roots, those functions are always going to be continuous on their domains. All right, that was it for this video. As always, please let me know if you have any questions.